Okay. Gracias.
It's a pleasure to present Sebastien Breteaux, which is going to speak now about quasi-classical reduced dynamics without ultraviolet cutoff.
Oh, thank you. So, well, I'd like to thank the organizer for a nice, very nice conference. And yeah, today I will talk about quasi-classical reduced dynamics without, well, with or without ultraviolet cutoff. And this is a joint work with Michele Correggi from Politecnico di Milano, Marco Falconi also from Politecnico di Milano, and Jérémy Faupin from Université de Lorraine. So before we go to the real problem, I'd like to speak a little bit about some spaces which are called Lorentz spaces and which generalize the Lebesgue spaces. So, and they also generalize the weak Lebesgue spaces. So here is the definition. So you consider some function on R to the D with values in C, measurable, and some number between 1 and infinity. And you consider also the decreasing rearrangement of a function f. So I will not give a precise definition, but it's actually a quite intuitive object. So let's look at the 1D case. Oh, maybe a bit more space. Yeah. If you have a function f, let's say it's positive, you want to bring all the mass to, you want to get a version only on the non-negative rails with a mass. So you want to have this mass where it's the highest, you want to bring it here. Well, actually it's bad because it needs to be non-decreasing. And with two functions, if you look, let's say, at the measure where it's higher than some number lambda, and it will correspond to, let's say, this area. Well, the measure of this set and of this one are the same. Okay? And yeah, so you get a version that is only for non-negative number and which is decreasing. So it's interesting because it keeps more or less it keeps most of the relevant information on function f from the point of view of measure theory. So you have two cases. So you see we have two exponents here for this Lorentz spaces, and you get some kind of a bit complicated expression here. But if you take, say, Q equal to P, then here you get T to the power 1, F star to the power Q, and the T to the power 1 here simplifies with this one. So you get actually only the LP norm of F star, which is actually the same as the LP norm of F. So it's a generalization of the LP spaces. And here, it's actually what is also called the weak Lebesgue spaces. But the Lorentz spaces encompass also this class of spaces. And what will be of particular interest for us is that the function 1 over k, which is in no Lebesgue space, it is in particular in these weak Lebesgue spaces. But we will also need the version with Q, which is not infinity. So let's go to some other properties of those Lorentz spaces. So I recall the definitions here. So first, there are quasi-normed spaces. That means they are not normed spaces. What fails is actually the triangle inequality. It fails, but not so much, because actually you get a triangle inequality, but with a constant here, which might be larger than 1. And also, it's quasi-normed, but you can find an equivalent norm in the, well, not for every P and Qs, but for the one we will be using, you can find an equivalent norm. You have some embeddings properties. If you have some any P and Q1 smaller than Q2, then you have this injection. And what I already said is that you can identify LPP with LP. You have several nice properties that you have already in LP space. You have an Holder inequality, which looks, well, really similar to the usual inequality. What changes is just that, well, for Holder inequality, the usual one, you have only 1 over P, oh, sorry, it should be P naught and Q naught. So you have 1 over P naught equal to 1 over P1 plus 1 over P2. And here you have the same relation for the exponents Q. So 1 over Q naught is the sum of over 1 over Qs. You also have a Young inequality. So the relation on the P's is the same as usual. But the relation of the Q's, you don't have a plus 1 here. You just have 1 over Q naught equal 1 over Q1 plus 1 over Q2. And here again, it will be P naught and Q naught actually. Okay, and you have some also some nice properties with respect to the Fourier transform. It's like the usual property of the Fourier transform continuity from LP with P smaller than 2 to LP with P larger than 2. Okay. And with this, so I will use these tools later in my presentation, but now let's go to the Nelson model and a reduced version of the Nelson model. So let me remark that I will present here all the results in the case of the Nelson model, but they actually, for simplicity, but they actually hold also in the case of the Pauli-Fierz model, which is more realistic and it's normally harder with the question of ultraviolet cutoff. So let's see, what do we consider? So, okay, here I will always consider x and k to be some numbers in R3. And U of x will be an external potential, so which will be real valued. And our system, we will consider a particle interacting with a field. So the quantum viewpoint is that we will have here first Hilbert space to describe the particle, and here another Hilbert space to describe the field. So we already saw it several times, but let me just recall a little bit how it works. So we have some particle for, well, some space for, let's say, one particle in the fields, and we have a symmetric tensor product, or tensor power of this field. And then we make the sum. So this, with tensor power n, is to describe n particles in the field. And this is the sum to be able to describe all the possible number of particles in the field. Yes. As far as I know, they were introduced by Lorentz, I think in the 50s. I'm not sure, but when exactly. But yeah. But not the Lorentz, of course, not the Lorentz of physics. Another one. Yeah, and so here is our Hamiltonian, which describes the system. So we have the kinetic energy of a particle. We have an external potential for the particle. And here's the energy of a field. So for photons, we have this K. Well, we could consider something more general, but for simplicity, I will just consider this type of function here. And this part describes the interaction between the field and the particle. And so here the energy of the field. So it's we already met it during this week, but let me remind how it works. So if you have a function psi n, let's say here for n particles in the field, so which depends on n variables in R3, you will get the energy of the first particle plus of the second particle and so on to the nth particle. And here we have some semi-classical parameter because I will consider some semi-classical parameter limit, but only in the field. And for the interaction, here we have what is called the field operators. So it's actually the sum of something called the annihilation operator and its adjoint, the creation operator. And I just wrote the formula for the annihilation operator, which is given here. If you have a symmetric function here, you just integrate one of the variable, and so you lose one of the n variables. You get only n minus 1 variables, and you get a function of n minus 1 variable, hence the annihilation. And the scaling here is square root of epsilon. So each time I have an annihilation operator or creation operator, it will always be with a square root of epsilon. And yeah, I will be, so this is the full Hamiltonian, but I will be interested actually in some reduced models, some simpler thing. So let me go to it. What I will be interested in is the energy on some class of states which are product states in sense of tensor products. So you have some, let's say, to simplify it, I will be a bit sloppy in the first slides, and I will precise the assumption later. But let's say psi is in L2 of x, or a subspace of L2 of x. And here you have psi epsilon, which is in, the Fock space, which is the space I introduced in the previous slide. So the space describing fields. And you consider the energy of such a product state. So you will get, I will consider that psi epsilon is kind of fixed, and I will consider it as a function of small psi. Okay, so here's this function. So this is for the kinetic energy of a particle, this for the potential, and here you get the energy for the field, and this whole part here is for the interaction. So the first line is actually quite simple, but you see already that I will need more condition on psi than what I just said. We need psi to be in H1, and we need also to have this integral, which makes sense. I will come back to this later. And what I'd like to do is to write this in a reduced form where you kind of really get separated the potential, the energy of a particle, the state of a particle and the state of a field as much as possible. So let's do a small formal computation for that. So here I just recalled the energy of interaction that we had on the former slide. And one thing we can do is we remark that there is an integral over x. And if we compute the integral over x, it's only this, which has x, and this. So you can actually make appear the Fourier transform of psi square. And that's what we did here. So here you have a Fourier transform of psi square. And then you have this, this part here, which is the part which involves the field. And a part with this function chi, but you can think of it as being a cutoff function. So it's a function between 0 and 1. It will just, if we need, we can cut some frequency. And for the original model, you will require that it does not go up to infinity. But we'll see that for the reduced model we consider, we can get it equal to 1. So this part in green, to simplify the notation, I will write it like that. With a small abuse of notation, it's not the same A epsilon K as in the first slide, but yeah, it's just notation for that, let's say. Okay, and now we will consider this this quantity here, and we will see what we need so that it on psi, small psi and large psi, so that chi, so that it makes sense. And I will consider it as a linear functional on psi square here. So let's study a bit this linear functional. So it's kind of an interaction term here. So I replace the psi square by some rho, function rho. And okay, here are the assumption we need on chi. So I just suppose it's in L3 infinity. So for example, we can take chi to be equal to 1, so no cutoff. And for psi, we'll just assume some uniform bond on the energy. And well, of course, the norm, we can think of it as being the norm of psi epsilon to be fixed equal to 1. But yeah, we actually just need this uniform bond. And okay, so let's see this term, which is actually the one of the interaction. We can actually write it as in a simplified form. So just the integral of some the function rho times the potential V. And this potential V is some, well, it's this Lorraine space, which are a bit abstract, but it's, well, I mean, just because we are not so much used to them, but actually they're not so much more abstract than Lebesgue spaces. And you can get also some estimates on this potential V with respect to, so P is actually minus E nabla operator. Okay, so yeah. Yeah, it's because here to make sense of the energy functional, I mean, I would like not to have any cutoff because it's, well, it's a very desirable property. And if you got L3, you cannot have 1 here. But if you take this weak Lebesgue space, weak Lebesgue space, you can get 1. So you're, well, no, you're happy about that. Yes. Yeah, so here I got this, I mean, I get the square root of k. If you can simplify 1 here. And so that's how we get 1 here. And this one is the one that you can control. You will be able to control from the hypothesis.
So what is A epsilon of k?
So
back one slide before, maybe?
Sorry? Let me go back to the slide. So, okay, either you can, if you know about the separators, it's what you think of, the one of a physicist, with not the L2 function, but just one in one point. But here it will be more simply, it's just this integral, that this integral here is just this one. So you have actually an integral, but over only n variables. And you have 1 here. It's not the same number of particles here and here. So you keep 1k here.
Okay, thanks. So the square root k has nothing to do with the scalar product. You can pull it out.
Sorry, the
square root of k, you can pull it out of the scalar product.
Yeah.
The last line.
Yeah, and so here I make a period 1 artificially, and I can put it wherever I want.
Okay, thanks.
Okay. Yeah, the scalar product is only on gamma on L2, and this is an additional variable which is in the integral here. Okay? Okay, so let's see a little bit how we can deal with such, how we can control this quantity with a property that we saw on the Lorraine spaces. So I just copied the expression from the previous slide here. And we are interested in controlling this, well, it will be a linear form, and we want to show it's continuous, basically. So we take the modulus, and the first step is just using Cauchy-Schwarz with a variable k. So we just split with this part, and yeah, it's just the product of two L2 norms. The second step is that we focus on this green term here, and we have a product, so we can use Hölder inequality, well, in Lorraine spaces. So if you check the numerology, you have 1 over 6 plus 1 over 3 is 1 over 2. And let me maybe recall. So L2, you can identify it with L22. So you want to have 1 over 2 is equal to 1 over 6 plus 1 over 3. And then you have, again, the over 2, it will be equal to 1 over 2 plus 1 over infinity. So it's fine. And the good news is that this one, well, it's finite from the assumption. So you can just forget about it. And this one, you have the properties of a Fourier transform. It's in the right direction. So it's, well, you have 1 over 6 plus 5 over 6, which is equal to 1. That's fine. And 1 over, well, then the 2, you just let it as it is. Okay, so here you're happy because you already have your estimate with respect to the right norm of rho. And so you still have to deal with this term. Well, again, you use Cauchy inequality. Well, this time we in the space with you have a sum here hidden, but you have the sum and the integral. And if you use Cauchy, you will get a norm of psi, and you will get this. I mean, it's a bit formal, but it would be just if I come back to slides before. It will be just this one with the square root of k, and you take the square. Okay, so let me come back. Okay, so you just actually get exactly the psi d gamma of k psi, which by assumption is bounded. Okay, so if we take everything, we have that the modulus of L epsilon of rho is smaller than rho to the in the norm L 6 over 5 2. And so we have a continuity. And so I did not precise it, but you also have some nice properties for duality in those Lorraine spaces. So it will be what you would expect, you know. The dual of this L6 over 5 2 space is L6 over 2. So you get a potential V in L6 over 2 so that you can write your thing as just an integral. So if we, so this will enable you to write your energy quadratic form with a nice potential instead of your potential in the, your function in the fields. And here, let me just briefly sketch how you get the bonds on this. You can get some nice bonds on V epsilon. And so if you want to get a bond of this type, so but it's relatively bounded with respect to this operator P to the 1/2, you will just take some psi 1 in L2 as a psi 2 in H dot 1/2 and estimate this quantity. And this you can just do the same estimate as before, and you will, again, by the same computation, you can bound it by the Fourier transform of psi 1, psi 2. And this time you have a Fourier transform of a product. So you can write it as a convolution product. And a convolution product, you can estimate it using Young inequality. So if you check the numerology, you would just get these norms here. So here you get the L2 norm of the Fourier transform of psi1, which is just the L2 norm of psi1. So this one, you will give this term. And you have to work on the green term. So the green term, you have L3 to infinity. So you can make appear k to the minus 1/2 and k to the plus 1/2 in front of it, and use again Hölder inequality. And this guy here will be finite in the Wick-Lebec space. And this guy here, well, this L2 infinity norm, it's smaller than the L2 norm. It's what I wrote here. And this one, actually, you recognize the H1 dot norm. So you just get very easily, if you use the property in the Lorraine spaces, you get this estimates. Okay, which is quite useful for in the analysis you get afterwards. Okay, so let me a bit summarize what we have. So we will need 3 assumptions. So the assumption of chi that we already saw, it's chi on the k is in L3 infinity. We have an assumption of psi, which is some uniform bond. And we need an assumption on u, which is here. So you split it in the positive and negative part. The positive part only needs to be in L1 lock. And the negative part, you have to be able to control it with respect to the Laplace operator with this kind of control here, with a smaller than 1. And with this assumption, you can define the following quadratic form on psi. So this is the kinetic energy of a particle. This is the potential energy of a particle. And this is the potential energy which comes actually from the interaction with the field. Okay, and you can define it on H1 into L2 of u plus dx. So this form is actually quite nice because with our assumption is symmetric, closed and bounded from below. And thus you can define a self-adjoint operator corresponding on domain d epsilon, which is included in Q. Okay. So now we would like to make epsilon go to 0. So we'll need some tools for the convergence. Just to know how much time do I have? $15 minutes. Okay. So let's look a bit at semi-classical convergence. So here you have slightly abstract definition. Anyway, you start with family psi epsilon of state in the fields, only in the fields, and you want to define probability measures on some space H alpha, which is actually just a L2 space but with a weight. Okay, so we need this weight because of the natural energy space for the fields, and we say that mu is a semi-classical measure associated with the family psi if you can extract a subsequence epsilon n such that these quantities here that you should think of as some kind of Fourier transform of psi epsilon. I will not give much more details. They converge to some quantity which is some kind of Fourier transform of the measure. So the convergence is kind of defined in terms of Fourier transform. Anyway, this is just the abstract definition. I will not use it in what follows, but it's just to say that we have a nice meaning for the notion of convergence between two objects which are quite different. Here you have vectors in L2, in the Fock space, so the space of sequences of states with any number of particles. And here you have a measure on this L2 space. But what I will be more interested in some properties that you have with this convergence. And we'll see that later. But okay, now that we know what kind of limit object we can use, so we'll have a probability measure on L2 of with some weight. And in this case, you can define a linear form, which is the analog of the linear form L epsilon we had, but in the limiting case. And I just give the formula here, but we could actually do more or less this, well, some very similar computation as before, and show that you can write this linear form as an integral. So you will have an effective potential V mu in the semi-classical limit, and with the same kind of estimates. The methods are the same as what we already saw in full detail. And you get the same kind of results if you get the same assumption of chi and u, and you set a measure mu. You can define thus an effective quadratic form in the semi-classical limit with the same kinetic energy and just the limiting potential. And you get the same properties. Your quadratic form is symmetric, close bounded from below, and then you get an Hamiltonian, which is corresponding to this one. Okay, so now let's see what I told you. The convergence properties, the definition, it was a bit abstract, but actually you can, what will be of use more is the last here convergence results, that if you have psi n and some a of g psi epsilon n, you can make it converge to something with a measure in on this L2 with a weight space. And this is basically the convergence that we will need. And yeah, maybe I've been a bit, yeah, sorry. Psi is not necessarily normalized, but you have a control still. If you can just forget about this one, you have psi, scalar psi, which is uniformly bounded. So you no, sorry, I forgot. No, you're right. This cannot be. Yeah, psi is normalized here. Yeah, psi.
The one is in the d gamma, or
sorry?
It's d gamma of 1 plus k, or are you counting the number of particles in psi?
Sorry?
Do you want to count the number of particles in psi? I mean,
but here for this result, is that you have this assumption, and plus you need here that psi is normed, because otherwise you have no, you cannot hope that it goes to 1 actually. And this your remark is yeah, I forgot an assumption. Your remark is already relevant here. I should have written psi normalized. Yeah. Otherwise, you have no hope that this will be a probability measure.
Thanks.
Okay. Yeah. So yeah, you have to think that this psi is normalized here. Okay. And yeah, so you get some. This is basically the convergence results that you will need. And yeah, so here is the theorem. And so you take all the assumptions that we got from before. So chi over k is in L3 infinity. You have some u with some control with respect to the Laplace operator. And here you have psi with the energy bounded and of norm 1. And you consider semi-classical measure associated with this family of states psi epsilon. Then you get that the quadratic forms describing your reduced model converge to the one associated with this semi-classical measure. in the sense of gamma convergence. And actually, this gamma convergence, it's equivalent to the convergence in the strong resolvent sense of the corresponding Hamiltonian operator, which is also equivalent to the convergence of the dynamics for strong convergence of the dynamic associated with that for all t. And if you add some assumption that the U is coercive, that is, it goes to infinity at infinity, then you can get a stronger notion of convergence in the normal resolvent sense. Maybe I should recall, well, just say what is the gamma convergence. So it's you have two properties that you want to prove. The first one is that you can find some sequence psi n which goes to some well, for any psi you can find a sequence which converges to psi, and with the limit sub of qn psi n is smaller than the q infinity of psi. And in the other direction, it's a bit stronger. Well, it will be for any psi in Q, and for any sequence psi n which converges to psi weakly, then you have to be able to prove this inequality. I will not have time to prove this gamma convergence, but instead, what I would like more to do is just give an overview of what you would do to modify the framework for the Pauli-Fitts model. And yeah, so you have a different model which is a bit more involved. So what changes is here this time you have both, let's say, the interaction which also encompasses the kinetic energy of the particles. So it's just mixed in this term. And I will not explain what is this A, but you can think of it some kind of quantization of magnetic field if you want. And here, sorry? Yeah, vector field. Yeah, you have here, hence the C dot, and these are the Pauli matrices. And here you have the assumption, so it's a bit modified, but here you have chi is in L infinity, which is still nice, because you can still have one. And here you need, for the control on the psi epsilon, that is the vector in the field, you need a stronger control. You need to control the energy at the order 2. And the assumption on U do not change, it's the same. Then you could define a reduced version of your A. So this is A without the double bar. So it's really just a vector field. I mean, it's with values in R3. You know, it's not. And you have here you have a formula, but yeah, let's not go. I mean, it's just to say that they exist, and you have to deal with this kind of formula with the same method as before. You have the same thing for the semi-classical limit. And you have also some results of convergence, but not only for the order 1 in the field, but also with some quadratic terms. You can also have some semi-classical results of convergence. Let's not get to the detail, but it's just, yeah, you have the same tools as before, but you can still use. And we get, well, exactly the same kind of theorem, just with modified quadratic forms corresponding to this setting. Here there should be some tilde, there and here, actually. Yeah. Okay. And yeah, so maybe let me just give a little bit of a view on. So for the gamma convergence, the results we use are in the book of Dalmaso from 1993. Maybe, yeah, I should have included some results on the, at least on the Lorentz spaces. I'd say that most results are quite elementary. The only one which is not elementary is the Young inequality, which is due to O'Neill in 1963, well, there's a mistake in the proof, so it was fixed in 1969 by Yap. And here you have a Marinier. Well, for the framework, exactly the same framework that I've given here, you can go to some works from of Anna Marinier between 2008 and 2015. Actually, there are several. It's a series of papers. And yeah, no, maybe let me present. This one is the one with the framework when you have some weighted spaces for the energy for function for the field. And this is actually more or less exactly the same as what we did here, but with cutoff, ultraviolet cutoff. And here we have the two other papers where we kind of used the same kind of ideas to get rid of ultraviolet cutoff, but for just in the study of ground state as products. And yeah, thank you for your attention, and again, congratulations, Vilker.
Many thanks for this nice talk. So any comment, question?
I have two questions. The first question is about the exponent 6/5 for rho. In the first estimate, you actually gave a proof. Yeah. Is borderline if you want to have that you can replace chi by just a 1 and still get a well-defined model, or is there space for the exponent to
so
vary?
to replace k by 1, I think it's borderline, but it's not borderline for the well. You could use here. I did not go further on that, but then for the actual convergence, you need this kind of estimates uniform, and in epsilon too. Well, uniform in epsilon. And here we are not at the border case in the Nelson model, but in the Pauli-Firth model, we are at the limiting case for these estimates.
Then I have another question concerning the Pauli operator you discussed at the very end. So there, this is, you remove the cutoff in the end, right? Or
yeah, I mean, this operator is not defined if we remove a cutoff. But what we can do is to look at some special states, and we remove also this energy part, and we just consider the energy on some special states that will maybe not make sense with a full operator, but the energy we can extend for some class of states. You can make sense of the energy of this operator, and then we can extend it once you have a quadratic form on the residue space. We can extend it with more general psi for the particle if we use the formula with a Fourier transform.
this is if you have U. If U, for example, is the hydrogen atom potential, the attractive, -1 over x absolute value, then it would be interesting to see how your result relates to the result of Loss and Yao from the late 80s, where they had shown that there's an instability. I mean, there's this. If you vary the classical magnetic field, then the infimum of the energy is -infinity. One can drive the particle into the nucleus, so to say. And that's special to the Pauli operator. It does not work for minimal coupling.
Do they consider only product states or more general states?
It's a classical magnetic field, so it's not quantized.
Yeah,
So in some sense, they just throw away from the last term, the d gamma of k absolute value. You could write this as gradient of a square plus a square and then an integral, I mean in a formal way, the harmonic oscillator energy, and then it would amount to even just throw away the gradient a square term. So it's purely a classical variation.
Maybe we can discuss about that because I have no. I mean, I did not think about it at
Okay.
all, but it will be interesting. Yes.
Yes, indeed.
Any other question? Comment?
Arno, yeah.
So thanks for the nice talk. So I did not understand, maybe you said it, what's the typical number of particles in the field?
1 over epsilon.
1 over epsilon. Okay,
Yes,
thanks.
it's yeah, I should have said that. That's good. Yeah, thank you for asking. And actually, you can kind of see it in the scaling here, because if you look at the number of operators, so you will have a star a. So you will have 2 powers of square root of epsilon. So it's then epsilon. And we ask that then you will get epsilon times n. And this we ask that it's bonded. So you can think of epsilon times n to be bonded. So n is of order 1 of epsilon.
Yes, thanks a lot.
Any other question or remark? I have one. The result of the Nessel model is weaker than when you get in polyfields. You can get in polyfields, you can get this polynomial in terms of A, right? You can A square. You get also correlation function with
But
A square and not with the Nelson model. I
yes,
did not have time really.
but we have a stronger assumption in the
polyfields with stronger
polyfields
assumption.
model. We have let me go back. Yeah, here we have this added assumption here, which allows us to have some convergence also for the squared for terms of order 2 in the field. Otherwise, we cannot do that.
Okay, now I understand. I overlooked this additional things which is in red. Okay. Thanks a lot. Any other question? No. If not, let's thank Sebastien again, and see you in half an hour.